everyone, and welcome to this midterm review session class. So, today, what we are going to do is we are going to go over some of the important concepts we have covered up to this point in our class. And I hope this review session helps everyone to prepare well for the exam. And of course, if you have any questions after this session, you can always email me, and I will be very happy to answer all your questions. So, let's get started.
The basic idea of the stiffness method is the divide and rule strategy. So what we do here is we take a structure and divide the structure into small pieces. Sometimes we call these pieces as finite elements or just elements. And the idea here is we can express the physics of individual element easily. So it's difficult to express the physics of the entire structure, but we can actually learn the physics of individual element. And at the end of the elements, sometimes we have these um, here I'm showing like red circles. Sometimes we call these ends as nodes, and we are referring to the element nodes all the time in our class. And nodes are actually the ends of the endpoints of the element, and that's where the displacements are described. So what we do is we can actually now express equilibrium condition for individual element. That's easy to do. So it's actually difficult to write the equilibrium condition for the entire structure, but for individual element, it's easy to write down the equilibrium conditions. So here, this is the equilibrium condition where PE is the force or the nodal forces, KE is the stiffness, and UE is the displacement vector, and POE is the element force vector that is coming from other effects that can be temperature, fabrication error. Uh, it's important to realize that this equilibrium equation is written for a single element. For each individual element, we are able to express the equilibrium condition in this fashion.
And finally, what happens after we write equilibrium for each individual element? We try to assemble the system. Assembly means we put all these equilibrium conditions from, for example, for element number 1 to number 8 and put it back together in the global form. And when we try to join them together, we are using the condition of compatibility to make sure that all the degrees of freedom are assembled in the correct way. And finally, we end up with a global system that has the same form as that for individual element. So we can write the global equilibrium conditions as P is equal to Ku plus Po. Again, here K is the global stiffness matrix. Use the displacement vector. P is the global load vector, and PO is the load vector due to other effects that might include fabrication or temperature error.
So this is now the overall strategy of the stiffness method, like what are the important steps that are needed in this method. So step number one is whenever you have a structure that is given, so first of all you have to discretize the structure. It means that you have to divide the structure into elements. And this typically includes you have to identify the nodes, where you want to put the nodes in the structure, and you have to label the corresponding degrees of freedom. And as we have discussed earlier, uh, you don't have to worry about labeling the degrees of freedom, but it's always important if you can choose a correct strategy. For example, especially for trusses and when we are doing problems with hand, it's always important to label the free degrees of freedom first and the supported degrees of freedom later. This helps just with the organization of the entries in the final stiffness matrix. And the next step is after we do the discretization is to determine the element stiffness matrices and the load vector POE for a single element. So here element stiffness matrix depends on the kind of element, and the POE vector for a single element depends on whether there is some additional effects, for example traction, fabrication error, or anything else that is acting on an element. And then we move on to the step number 3, and for the step number 3, what we are trying to do here is we are trying to assemble now the global stiffness matrix and the global load vector. Again, the PO vector comes from temperature and fabrication effects, and the stiffness matrix is actually coming from the individual element stiffness matrices. So you have to make sure that you are trying to actually assemble them in a correct fashion. And the step number 4 is then taking the system and applying the boundary conditions and the support conditions. So when I say the boundary conditions, means you applying the load on the structure, like the nodal loads that are given to you, and the nodal support conditions. Some of the support might be also moving. For example, you might have a support that has a movement, or a lot of times a lot of supported degrees of freedom are just fixed, so it means that they cannot move, and those corresponding values are 0. And finally, we solve the system after applying the boundary conditions. So by solving the system, you'll get all the unknown displacements, and then we have to back substitute those unknown displacements to find the support reactions if needed. And this actually completes the solution process. And sometimes you also have to calculate member forces, and for that you will need to use the nodal displacements again to back substitute and find the element forces. So this is the overall strategy of the stiffness method, and this idea is applicable to any kind of structure that we are going to work in this class. Actually, this is practically all the important steps in the stiffness method. So if you are able to follow this step, you actually understand the method correctly.
This slide explains the solution by the stiffness method. So here again, we are looking at the system, global system. P is equal to Ku plus P0. So this is our global system here. And so here K is the global stiffness matrix. We have to remember certain properties of the stiffness matrix. So K is a singular matrix, as we have discussed earlier. It means that determinant of K is 0. So we never take the inverse of the K matrix, or we never take the inverse of the global stiffness matrix. Another important property of the stiffness matrix is that this global stiffness matrix is a symmetric matrix. This means that K is equal to K transpose. Here again, use the displacement vector. P is the nodal load vector, or some of the nodal loads are actually support reactions that are unknown, and P0 is the nodal loads due to distributed traction, fabrication error, and temperature effects. And the idea is we want to solve the system. Typically, when we are solving the system, we try to use the block solution approach. And the idea here is we label the degrees of freedom as F and S using the subscripts. F here stands for free degrees of freedom, and S are the supported degrees of freedom. So we can actually partition U into free degrees of freedom and the supported degrees of freedom. Similarly, the P vector is actually partitioned into PF and PS. So PS are the support reactions that are unknown. PF are the nodal loads. So these are given. P0 is the vector due to other effects. So this again comes from temperature, fabrication, traction, and so on and so forth. And similarly, we can partition K into this block matrix form. And then actually we can put the system nicely in this way. And if we are actually labeling the free degrees of freedom first, we never have to partition it. The system is automatically partitioned for us. So it depends on how you're trying to solve the problem, or how you're labeling the degrees of freedom. It's always sometimes a good strategy to label the free degrees of freedom first and supported degrees of freedom later on. So the system is automatically partitioned in this form. With this form of partition, actually, we can go ahead and solve the unknown displacements and the unknown support reactions. And the strategy is we write down these two equations. So the first equation is using the first PF is equal to KFF-UF plus KFS-US plus POF. So this is our first equation. And the second equation comes from the second block here. This is PS is equal to KSF-UF, KSS plus KSS-US plus POS. So this is our second equation. So there are two equations written in block matrix form. And the idea here is we first solve for UF, and then we go ahead and solve for PS. So we just solve for UF first. If we are trying to solve for UF, we just rearrange these terms, and this is the solution here. So in this case, you can see that we need the inverse of KFF portion of the global stiffness matrix. Again, we don't have to invert the entire K stiffness matrix, but only the KFF portion. And if the system is formed correctly and if it's supported correctly, then KFF should be invertible. So we should be able to find UF for a given system. And after we find the UF, we take this UF and back substitute in this equation, the second equation here, to find the unknown support reactions. So this is the equation for finding the support reactions, or PS. Some important remarks that I would like to add. One important thing is to realize that because of the symmetry of the stiffness matrix, KSF is equal to KFS transpose. So this portion is a transpose of this portion. And the another important thing is sometimes US is 0, or all the supported degrees of freedom are 0. And in this case, we don't need to assemble KFS or KSS, because you can see that KFS is getting multiplied by 0 and KSS is also getting multiplied by 0. So they are not needed actually in the solution process. So this is if you are working for the exam, so it's important to make sure that you are just assembling the correct entries that are needed for the solution process. So this is just a small example to show you the idea here. So what I have done is I've created a 6x6 system, and written in the block matrix form. In this case, the free degrees of freedom are U1 and U2, and the supported degrees of freedom are U3, U4, U5, and U6. And what I'm assuming that U3 and U6 are 0, so they are prescribed to be 0, while the U4 and U6 are non-zero. So U3 and U5 are 0, and U4 and U6 are non-zero. And we want to solve the system. And in this case, we just want to find the unknown displacements and the support reactions, that is P6. We are not interested in finding all the support reactions, but just one of them, let's say P6. So to find the UF, this is the relationship. So this is exactly the relationship for finding the unknown degrees of freedom. So this is KFF. Here KFF is 2 by 2. This is KFF inverse. This is PF minus KFS US minus POF. These first two entries belongs to POF. So you have to include these in the solution process. And finally, we need this portion, KFS US. KFS US is actually the contribution of this block multiplied by this vector here. But as you can see that because U3 and U5 are 0, they get multiplied by K1, U3 get multiplied by K13 and K23. So you don't really need these K123 and K13 and K23 because it's getting multiplied by 0. Similarly, K15 and K25 is also getting multiplied by 0, that is U5. So you don't need these two entries. So what this calculation KFS US can be simplified into just using these four numbers, K14, K24. So we can take this and multiply it by U4 plus K16, K26 multiplied by U6. So this algebra can be simplified in this form. So this is an important observation because you don't have to assemble the entire KSF portion. You just need these four entries. So finally, you can after you put all the numbers together, you can find the unknown displacements that are UF, U1, and U2 that constitute UF. And after solving for the unknown displacements, we can go back and back substitute to find P6. So this is the calculation for P6. If you look at the P6, we are only interested in finding P6. So we just have to look at the last equation here. So you can see that P6 is equal to K61 times U1 plus K62 times U2, and then so on and so forth. And if you do this calculation in a smart way, you can figure out that K61 and K62 is getting multiplied by U1 and U2, that is UF. So we can write this in matrix form as follows. So we can just say K61, K61, K62 multiplied by U1 and U2. And U1 and U2 is UF. Plus, we have to take some other terms in this block here, but in this way, we can also do some of the calculations smartly. We just need, in this case, K64 and K66, because only U4 and U6 are non-zero. So we just want to add the contribution of non-zero terms. So this is going to be K64U4 plus K66U6. Remember that K63 U3 is going to be 0 because U3 is 0. Okay, so U3 is given to be 0 here. So that term is not needed. Similarly, K65 times U5 is 0 because U5 is 0. It doesn't matter what K65 is, or it doesn't matter what K63 is. Those numbers are getting multiplied by 0. So this is an important observation when you're doing some calculations for the exam. So make sure that you just do them in an efficient way. Of course, you have to add this PO6 vector, PO6 entry here. So this is the entire calculation for the support reaction P6. Moving forward, now we want to talk about some of the element stiffness matrices and some of the these PO vectors we have worked with. The first element that we have worked with was a spring element. So this is the most simplest element. So in this case, this was a one-dimensional spring element, and in this case, this element has 2 degrees of freedom, I node and J node. There is a degree of freedom at I node, that is Ui, and the degree of freedom of J node, that is Uj. And the spring element stiffness matrix was written in a simple form. Let's say this is a K, and this is the spring element stiffness matrix. In this case, the K here is the stiffness of the spring. So this is a given number. So this is a physical property of the spring itself. And if you think very carefully, the units of this K is force per unit displacement. So this is actually the force required to displace or to deform the spring by a unit displacement. And finally, we can relate the forces to the nodal displacements using this relationship. So this is always the case, no matter what kind of element it is. So force is equal to the stiffness matrix times the displacement vector. In this case, these are the 2 nodal forces, and these are the 2 nodal displacements, and this is the stiffness matrix. Similarly, we have also derived the stiffness matrix for the bar element. It's practically similar to the spring element, and this is the bar element stiffness matrix, where in this case, the bar has the uniform area. So the cross-section area of the bar is not changing, and we are assuming that modulus of elasticity of this member is also not changing. So E and A are uniform along the length of the member. And this was the expression we derived in the class. In this case, you can think that the equivalent K for this, so you can think that this bar member is like a spring member, but the K value is actually EA by L. So sometimes EA by L is also known as the stiffness of the bar member, but when we talk about stiffness matrix, it's a 2x2 stiffness matrix. So this is the stiffness matrix, and we can actually express the member nodal forces Fi and Fj in terms of the nodal displacements Ui and Uj using the stiffness matrix. So this is the element stiffness matrix, and the force and displacements are related by the element stiffness matrix. We also talked about bar element with non-uniform area. So in this case, what we have considered a bar with a non-uniform area. So the area at the end I is different from the area at the end J. And we assume that the area is linearly decreasing or increasing. So, and we derive the stiffness matrix of this kind of bar element. So if you recall from our derivation, this is the stiffness matrix. So it has a very similar form if you compare with the spring or the uniform bar element. The only difference is this K value. So if you recall, the K is given by E multiplied by AJ minus AI divided by L log of AJ divided by AI. And here AI is the area at node I and AJ is the area at node J. Another important observation is it doesn't matter which, you can actually switch the thing, entries here. You can say E by L AI minus AJ log of AI divided by AJ. So both of the calculation will give you the same answer. And finally, the forces can be again expressed using the stiffness matrix. This is the stiffness matrix, but you have to make sure that you use the correct value of K, and the K is given by this expression here. So these are the three one-dimensional elements that we have discussed in the class. They're very straightforward and easy to use, and I hope that everyone is able to understand them. And if you have any questions about the element stiffness matrices, you can always email me and I will answer any of your questions. Finally, we have also considered traction, temperature, and fabrication effects. And the idea here was, when we are considering these effects, we fix the member ends and we calculate the support reactions that is caused by these effects. So we did the calculation for the three cases. In one case, we applied the uniform traction. So there is a uniform traction applied along the length of the power member, and this traction value is tau. So you can think like tau has the unit of force per unit length. So traction is like a force per unit length. So it's like a force acting on a unit length of the member. And we showed that the support reactions or the fixed end support reactions are FIM and FJM. So FIM is the force at this node and at the node I, and FJM is the force at the node J. And these are the numbers. So minus tau L by 2 and minus tau L by 2. So what is happening? Tau L is the total force on this element. I'm assuming that length of the element is L. So, and half of the force is going here and half of the force is going here. So this is very straightforward. So finally, we also consider temperature and fabrication error. And this is the force vector due to temperature. And in this case, you should remember that if the temperature of the member has increased above the ambient temperature, then delta T is positive. And if the temperature has decreased below the ambient, then delta T is negative. So this was the sign convention that was built into this equation here when we derived it. And we have similarly considered a case of the fabrication error. And the idea of fabrication error is that the member was like either created too long, in which case delta L is positive, or too short, in which case the delta L is negative. So depending on if it's too long or too short, these are the fixed end reactions of fixed end forces. And we have also derived this in the class, so you can always go back and check the previous slides for the calculations. But these are the three cases we have considered, and they all contribute to that PO vector. So remember that they all contribute to the big PO vector for the global system. And the idea is as follows. So finally, what we do is we use the principle of superposition here. So we said that we're going to say that the forces, the total forces, so Fi and Fj are the total forces. And these are the forces due to displacements, tractions, temperature, fabrication, and everything, all the effects. By using the idea of superposition, we are going to express these forces as the sum of individual components. So the total force is equal to the force due to displacements plus the force due to traction plus the force due to temperature effects plus the force due to fabrication error. And we all add them all together. So we take this is the Fi and Fj are the total forces. So total forces equal to the force due to displacements, force due to tractions, force due to temperature, force due to fabrication error. This is the addition. So this is the addition of all the forces. Force due to displacement is nothing but stiffness matrix times displacement vector. So this is the force due to displacement, force due to traction, force due to temperature, and force due to fabrication error. So you have to remember that not every member will have all the effects. So sometimes these terms, these three additional terms might be present or might not be present. So it depends on the problem that is given to you. So whenever you're doing a problem, be very careful to include these effects whenever they are present in an element. So let's go over one of the example, and this is actually the one of the example we have already covered in the class before, but I want to still go over it because I think this is a very important example, and actually it includes all the important concepts that I want you to remember, at least for this bar systems. So in this case, we have a structure which is composed of three elements, and I'm calling those elements as A, B, and C. And the properties of the elements are given. So A is a spring member, B is a bar member, C is also a bar member. The area of member bar B and C are different, and the spring stiffness is also given to us. So it's like 250 kip per inch. And the length of these bar members is also given. And there's a traction on the bar member B. So bar member B has some traction acting on it. Its value is 0.2 kip per inch. And finally, member number B is made 0.04 inch too short. So there is a fabrication error in member B. Member C is made 0.02 inch too long. So there is a fabrication error also in member C. And there is a temperature change in member C. So it's given to us that temperature of member C increased by 50 degree Fahrenheit above the ambient. And for this problem, we want to find unknown displacements, support reactions, and member forces. So if we go through the step-by-step process, the first step is to discretize the system. So in this case, we are going to discretize the system into three elements. So one is the spring element, this is the second element, and this is the third element. And we identify the nodes. So these are like 4 nodes, 1, 2, 3, 4, and we put the degrees of freedom. So this is the first displacement, second displacement, third displacement, and fourth displacement degrees of freedom. So there are 4 degrees of freedom, U1, U2, U3, U4, and the corresponding forces are P1, P2, P3, P4. And after this, we want to go to the second step and find all the element stiffness matrices and PO vector for every element. So this is the step where we find the element stiffness matrices and the member fixed end forces as needed. So remember that not every element will have this fixed end forces. So this is the stiffness matrix for the element number A or member A. Here, this is the stiffness matrix. And in this process, when we are writing the stiffness matrix, we also put the degrees of freedom. So this is the UI degree of freedom. This is the UJ degree of freedom. UI in this case was U1 and UJ was U2. So I label the degrees of freedom as 1, 2, 1, 2. For member number A, there are no fixed end forces. So PO vector is not there. So there is nothing else to calculate for this member. For member number B, this is the stiffness matrix for member number B. So it's like just 1,000, and entries are just 1,000, and with the minus or plus sign. And again, we have to label the degrees of freedom. So in this case, this is the UI. UI is the U2 degree of freedom. UJ is the U3 degree of freedom. So this is UI and UJ. So UI is 2 and UJ is 3. So 2 and 3. So this is important labeling. So make sure you label them correctly. Finally, on this member, there's a traction, and there's also a fabrication error for this member. So we have to assemble the PO vector for this element. So so PO, this is the traction, this is the contribution for fabrication error, and we just calculate these 2 entries and add them together. And if we add them together, this is the numbers we are going to get, minus 60 and 20, and make sure to label them. So the labeling is the same. So this is the UI is the 2 degree of freedom and second degree of freedom, and UJ is the third degree of freedom. So we can put 2 and 3 here. Finally, this is the member C. In this case, this is the stiffness matrix. Calculation is simple, but again, make sure to label the degrees of current freedom correctly. UI is the U3 degree of freedom. UJ is the U4 degree of freedom. So we're going to put 3 and 4, 3 and 4 here. Finally, the PO vector for this element is the contribution of fabrication error and temperature effects. Remember, for this element, there is no traction, so you don't have to worry about the traction, but you have to add these two contributions. So after we do the algebra, we figure out these two numbers, and these two forces go to 3, 4 degrees of freedom. And just remember that these 3, 4 are actually the same numbers as here, 3, 4. So once you figure out for this matrix, the same degrees of freedom goes for the PO vector. One important thing to remember that in this case, delta L, because the fabrication error was too long, so delta L was a positive entry. So it's like delta L is plus 0.02. And similarly, the temperature has increased, so delta T was positive 50. So make sure that you follow the correct sign convention for a given problem. So this concludes all the calculation for a given elements in this system. And finally, we can take all these calculations and assemble into a global system. And since we have all these numbers like 1, 2, 1, 2, 2, 3, 2, 3, actually this labeling helps us to assemble these entries into the global system. So this is the assembly into the global system. We have discussed this assembly process. We start with a blank matrix, and we add the corresponding entries from element stiffness matrix to this global stiffness matrix. So this you have to do very carefully. Make sure you don't do any mistake. So during this process, this is the final assembled system. And in this case, if we have to apply, we are trying to solve the system, we have to apply the correct boundary conditions. So for this case, U1 is 0 and U4 is 0. So these are the boundary conditions, and these were given to us. For example, if I go back, so you can see that U1 is 0, U1 is the boundary condition here, and U4 is the boundary condition here. So U1 and U4 are 0. And this, the applied load at the second degree of freedom is -100, and the applied load at the third degree of freedom is 0. So there is no load at the third degree of freedom, that is here. So third degree of freedom is here. There is no load here. So you can think that P2 is -100 and P3 is 0. So P2 is -100, P3 is 0. P1 and P4 correspond to the supported degrees of freedom. So these are unknowns. So P1 and P4 are the support reactions. And after we put all these values here, assemble the stiffness matrix, and also assemble this PO vector. So PO vector is the assembly of the POE vector that comes from every element. So we just assemble all the contribution for different elements, and we have to add the corresponding entries together. Okay, you start with a 0 vector and add the contributions for each individual element. So we have the system in this form. And finally, we go back and solve the system after we have assembled everything. Again, we want to write in the block form. So we can take the system and put in this block form here. And after we put in the block form, we can solve the system. So you can see that in this case, the 3 degrees of freedom are U2 and U3. And we have to find the corresponding blocks for this kind of partitioning. And the supported degrees of freedom are U1 and U4. So because U1 and U4 are 0, we don't need US is 0 here. So US is U1 and U4, they're 0 here. So we technically don't need KFS. So this is the partitioning for this system. So PF is P2 and P3. This is P2 and P3. KFF is the entries that comes from 2 and 3. So this is this block here that is coming from 2 and 3, 2 and 3 block here. And KFS is this block, US is 0, 0, POF is minus 60, 160, and then so on and so forth. So this is the calculation of UF, and we can calculate the UF and we can get the solutions here. This is U2 and U3. This is our solution, unknown displacements. And after we have the known displacements, we can back substitute to find what are the support reactions. Support reactions are P1 and P4. So PS is P1 and P4. This is KSF UF. So UF is the displacements we have just solved. We multiplied by KSF. We don't really need KSS because US is 0. So this is going to get multiplied by 0, but we will need POS. So POS is 0 and minus 140. So this is 1 and 4. So POS is 0 minus 140. And we do this calculation to find P1 and P4. So we can go ahead and do this calculation. This is the calculation for P1 and P4. And you can still see that KSS is getting multiplied by US, that is 0. So we don't really need this KSS here. But I'm just showing here for completeness. And this is our answer for P1 and P4. And if we put everything together, we should be able to see that the system is under equilibrium. So if you add P1 and P4, it's actually balancing out the applied load here. That is 100. So this is just a check. Sometimes you want to do a quick check to see whether your solutions are correct or not. So this gives you a quick check whether the system is under equilibrium or not. And after this step, we can go back and find the member forces. And in this case, when we are talking about member forces, we want to find Fi and Fj. So we just want to find what is this Fi and Fj. And remember, we already have a relationship. Fi and Fj is stiffness matrix times the displacement vector plus other effects if they are present. So for the spring member A, there is no other effect. So we take the stiffness matrix multiplied by the displacements. So for this case, UI is U1, Uj is U2. So UI is U1 is given to us. That was 0 because this support was fixed. And U2 is the calculation we have done, and we get the answer here. So you can see that looking at it, we can see that this force in the spring is 25.45 compression. So actually, the second component, the sign of the second component gives you whether it's a tension or compression if there are no fixed end forces, or if there are no distributed tractions. And we'll come back to this point in a moment. So this is the second case. For member C, these are the forces. So forces are Fi and Fj, stiffness matrix times the displacements. But in this case, we have to add the PO vector. So in this case, the PO vector was the contribution of fabrication error and the temperature. So this was the total contribution, 140 minus 140. So we have to make sure that that you add this contribution. And if we do the calculation, this is the member force. Fi and Fj is minus 34.55 and 34.55. So if we draw the free body diagram, you can quickly see that this member is under tension, and the tension is 34.55 kips. For member number B, the things are a little bit more interesting. So in this case, the distributed traction is acting on the member. So I have shown here the distributed traction acting on the member. So we can do the calculation again to find the member end forces, or the nodal forces at the end of the member. So this is Fi and Fj. So the calculation goes as Fi and Fj is stiffness matrix times the displacement vector for this element plus all the PO vector. So this is the PO vector. And these are the member end forces. So we can draw. Now it's very interesting. You can see that Fi and Fj is not canceling each other, because they should not cancel, because there is a distributed traction acting on it. So if you think very carefully, if we add them together plus the contribution of this traction, then you will see that the member is under equilibrium. And in this case, the force along the length of the member is changing, but we can draw a simple free body diagram to find what is the force in the at a particular location in the member. So this is a simple calculation. For example, The traction here is given by 0.2 kip per inch, and we can take a small portion of this bar and draw a free body diagram, and I'm denoting the force at the location x by fx. So the force here is fx, traction was 0.2 kip inch, and this is the fi force here that we already calculated, minus 74.55. And then I just wrote the equilibrium equation for this small piece here. So sum of all the forces in x direction should be 0. So what I am doing is just adding all the forces. So this is fx plus 0.2 times x. So this is the contribution of this traction plus this force. So plus this force here is equal to 0. And we can solve for fx from this relationship. So fx is this equation here. And using this equation, we can plot the distribution of force within this member. So now what I've done is I've just plotted the distribution of force. So though you can see that the force is linearly changing in this member. So force is always tension. It changes from 74.55 at the end I to 34.55 at end J, but the member is always in tension. And this concludes the example number 1 for our class or for the session. Next, I want to go over 2D truss element that we have covered in our class. So for the 2D truss element, this is one truss element in which this is node I and this is node J, and the theta determines the orientation of the bar member or this truss member. In this case, this element has 4 degrees of freedom. At the I node, the degrees of freedom are Ui and Vj. And the J node, the degrees of freedom are Uj and Vj. So Ui is the displacement in the x direction. Vi is the displacement in the y direction at node I. And Ui and Vj are the displacement in the x and y direction at node J. And Pxi, Pyi, Pxj, Pyj are the corresponding forces. So these are the forces in that corresponding directions. And we have shown that we can express these nodal forces in terms of nodal displacements by using this matrix here. This is a 4x4 matrix, and this is the truss element stiffness matrix. And this 4x1 vector is all these nodal forces here, and this 4x1 displacement vector are the nodal displacements for this member. So in this case, for a 2D truss element, we can see that there are 4 degrees of freedom for each element. You have to be careful when we are doing the calculation for the stiffness matrix for a truss element. You can see that there are only 4 individual unique entries. So there are only 4 unique individual entries that are C square, S square, CF, and rest are repeated. So this block is repeated in here, and this block is just the negative of this block, and this block is same as this block. So this is not complicated calculation. You have to just do C squared, CF, and S squared. So 3 numbers, and you just fill it up together. And make sure that you multiply it by A by L. So this coefficient is always there. L is the length of the member. A and E are the properties of the. So A is the cross section, and E is the modulus of elasticity of the material. Of course, you have to get the correct orientation, and we have gone over many examples to describe how to get the correct angle theta. So make sure that you get the right angle theta, and you put the right angle when you're doing calculation in your calculator. So just be careful to remember whether your calculator is working in radians or degrees, so you don't make a mistake in this calculation. Next, we can also include the temperature and fabrication effects. And we have calculated these temperature and fabrication vector. So these are like the fixed end forces. So this is the fixed end forces due to temperature, and these are the fixed end forces due to fabrication error. And finally, what we can do is we can use the principle of superposition to write the equation for a single member, including all effects. So these are Pxi, Pyi, Pxj, Pyj are the forces or the nodal forces for a single element, and this is the stiffness matrix. So what we are writing is we are saying that nodal forces is equal to stiffness matrix time displacement. So this is the first term is the contribution of displacement, second term is the contribution of fabrication error, and the third term is the contribution of temperature effect. Again, make sure that you remember that for the fabrication or temperature effect might not be there. It depends on the member. So these two entries might be present or might not be present. Finally, after we solve the system, and if you want to find the member forces, for the case of truss, we have derived this equation that gives a single number for a truss member. And in this case, we can calculate force as A by L multiplied by these row vector times the column vector. So this is just the displacement vector. And this is the row vector of C minus SCS. And we have to, again, include the contribution of fabrication error and the temperature effects. So make sure that you include these two entries when you're doing the calculations. So again, I want to go through one of the examples that we have considered earlier in class. And I again want to go through this example because I think it has all the important ingredients that you want to remember for the exam. So this is a truss structure with 3 members. And in this case, we have member AB in which there is a fabrication error. So this member AB was made 0.02 meters too short. Member AC was made 0.02 meter too long. So AC also has fabrication error. And the temperature of member BC, so BC is this diagonal member, increased by 100 degree Fahrenheit above the ambient. So I'm trying to include like different effects and different members, so you get an idea how to solve this kind of problem. Some properties are given to us. E is given, alpha, the coefficient of thermal expansion, is given, and the member areas are given. And again, the first step is to discretize the system and assign the degrees of freedom. So this is the way. So we discretize in this case into 3 members, and I label the degrees of freedom. So you can see that I'm labeling the free degrees of freedom first. If you think very carefully, there are only 2 free degrees of freedom in this case. So one is this vertical motion here. The second is this vertical motion here. All the other degrees of freedom are supported. So I label the free degrees of freedom first. So this is U1, U2. And then I can just go in any order. So I'm saying this is U3, U4, U5, U6. So this is the degrees of freedom labeling for the system. I again want to emphasize that I have labeled for the truss, the free degrees of freedom first. Now we go to the second step and we find the element stiffness matrices and the PO vector. So we have to go and make sure that look at a particular member and see if there is a temperature or fabrication effect in the particular member, and make sure that assemble the corresponding vector. So this is member AB. So AB was the horizontal member. So this was the I node, this was the J node. And these were the degrees of freedom, 5, 6, 4, 2. So orientation angle theta for this member is 0. Cos of theta is 1, sine is 0. So this is the stiffness matrix. And the labeling goes as UI, VI, UJ, VJ. So UI, VI. UI is this, VI is this. So this is 5, 6, UJ, VJ, 4, 2. So this is important. You have to get it right. 5, 6, 4, 2. Finally, we have to assemble for this member the fabrication error. This is the calculation for the fabrication error. And just make sure that delta L is, because this was too short, so you can see that delta L is negative here. And we did the calculation again using the CNS that we have calculated here. And these are the numbers we get. And the labeling, the label degrees of freedom remain the same. So because they follow the same order, this is 5, 6, 4, 2, 5, 6, 4, 2 here, and 5, 6, 4, 2 here. So You can think that this is the equilibrium for this element. So P is equal to KD plus PE. This is the equilibrium of a single element. Of course, we don't know D, so we want to find the displacements for these elements. That's a whole. For member number BC, we find C and S again. So C is minus 3 by 5, S is 4 by 5. So in this case, we are calling this as I degree of freedom, this as J degree of freedom. And so you can see that the ordering, this is the stiffness matrix, the ordering should be UI, VI. So this is 4, 2, 3, 1, 4, 2, 3, 1. So we have to get the correct ordering here. And for this member, there's a temperature effect. So we have to include the effect of the temperature and do the right calculation. In this case, delta T is positive because the temperature has increased over the ambient. And this is the calculation. We finally calculate this vector and put the corresponding degrees of freedom. So these entries goes to 4, 2, 3, 1 degrees of freedom. And they are actually the same numbers that are here. And this is the last member for this structure, member AC. So I node is here and the J node is on the top. And theta is 90 degrees. And the ordering for this should be UI, VI, UJ, VJ. So 5, 6, 3, 1. 5, 6, 3, 1 is the ordering of the degrees of freedom. And for this member, there is a fabrication error. So we have to include the fabrication error term here. And delta L here is positive because this member was made too long. So delta L, make sure that the sign is done correctly here. And the degrees of freedom are in the same order, 5, 6, 3, 1. And after we have all these quantities, we can assemble everything into a global system. And you can see that this assembly is a tedious process. So, but this has to be done very carefully. So this is the entire assembly of the system. Here, this is the PO vector, the global PO vector, and this is the sum of the contribution from element number AB, BC, and AC. So all of these, you have to add them together in the correct order. So this is the calculation. And after we do all this calculation, we can solve the system. So for this case, UF is actually U1 and U2, US is U3, U4, U5, U6. So these are all 0. So this is 0 actually, and P1 and P2 are just 92 and 72. So interestingly, we don't need this this block, but I have showed the entries here just for completeness, but we don't need this block because this block get multiplied by all 0 here. These are the different blocks I'm showing for the system, and we want to just solve for the known displacements or the support reactions. So if we try to solve for the unknown displacements, the calculation is simple. Just we have to realize that in this case, US is 0. So KFS US, this term is 0. So this is actually, this calculation is not needed. So we just need to put KFF inverse PF minus POF. So this is the calculation, and we can get U1 and U2. So this is the calculation of U1 and U2 here. And next, we can back substitute to find what the support reactions. So support reactions are PS, and this is KSF UF. We have calculated UF, so we will need KSF. So this is the KSF multiplied by UF plus POS. We don't need KSS because US is 0. So this contribution is again 0, but we have to add POS. So after we do this calculation, we can find the support reactions. So these support reactions are P3, this is P3, P4, P5, P6. After we find the support reactions, if needed, it depends on the problem. If the problem says you have to calculate the member forces, then you have to calculate the member forces for that given problem. Sometimes I will not ask you to calculate member forces for all the members in the exam, so you have to be careful. Just don't do calculations that are not needed. So in this case, let's say the member force in member AB is, we have the expression, we have to just plug in the right entries. So A by L times the first contribution. So this is just the contribution of displacement, fabrication, and temperature. In this, for the member number AB, there is no temperature, so delta T is 0, but delta L is there. So delta L is minus 0.02 because it was made too short. So this is the calculation, and you get the member forces. One important thing is you have to make sure that you're using a consistent unit system. So in this case, this is like this unit is meters here. So I have not shown the unit, but I'm using a consistent unit system here. For member number BC, here this is the same expression. We have to plug in the right entries. In this case, delta L is 0, so there is no fabrication error, but delta T was 100. Actually, it's plus 100 because remember this temperature was increased above the ambient. So temperature is increased above, so it means we have to make sure that we are using the correct sign. In case if the temperature has decreased below the ambient, then we are going to use a negative sign for that entry. So we did the calculation as follows, and we finally get the answer that is negative 90. So negative means this member is under compression. What if this was a positive number, then this means that this member is under tension. So this is the calculation for the last member AC. For the member AC, there is no temperature, but there is a fabrication error that was too long. So in this case, delta L is positive. So this is 0.02. And we are going to do the calculation, and we will get the number 164 kilonewtons. And in this case, the positive sign means here there is a positive sign. So this is actually tension. So these are all the calculations that you have to go through for this example. And these two examples that we have considered, they are like very comprehensive, and they include like different ideas that you might want to remember for the exam. And this actually concludes this session today, but I also want to emphasize on few important things here. You can always think before solving a problem what calculations are actually needed for a given problem. So if I go back, this is always the system that you are going to solve in our class. This is always the case. So you will have some unknown displacements, some supported displacements, and this PO vector might be there, might not be there. And these are the support reactions that are always unknown. And these are the nodal forces that are given. So this is always the case. So always remember that whenever you are solving something with this method, you always need to have KFF. KFF is always needed, because KFF is needed is to find the unknown displacement. So you always need KFF because you need to calculate the inverse of KFF to find the known displacements. So this portion is always needed. Second, if we look at the other entries, they might be needed or might not be needed. So as I have emphasized, if US is 0, so if this portion is 0, we don't need this portion because this portion always get multiplied by 0. And actually, KSS is also not needed if US is 0. So you can actually do selective algebra depending on what are the values in US. In this example that I have covered earlier, U5 and U6 were non-zero. So it means that we only need the fourth and sixth column. So it corresponds to the fourth and sixth entries. So it's easy to remember which columns are needed. So if we know that U4 and U6 are non-zero, it means that U4, fourth column, and the sixth column will be needed in the solution. So these are the important things that you want to remember when you're doing the calculations by hand for the exam. So you're not doing just extra calculation like multiplying by 0 and things like that. And I think if you have any questions, if you have further questions, or if you want any other clarifications, you can always email back to me, and I look forward for your questions. And actually, this is the first time I have created this online video. So I'm not sure how good I am at doing this, and but hopefully with some practice I will get better. And if you don't like this video, if you have any comments about this video, you can always email me, and I will try to improve the quality of video or the quality of sound or whatever if there's some issues. And with this, actually, I also like to share some of my delights that I should have shared actually at the start of the session, but um, I know it's a difficult time for all of us. But when I read a lot of news or listen to a lot of news, I don't find uh, much delight at this point. But I still think that there are like we have to like find some delight in our life, because actually this is the main thread that connects, I think, everyone, and it connects the humanity together. um, so these days actually I find delight in talking to my friends all over the globe, and I have friends everywhere in every part of the continent or every part of the earth. So these days I talk to my friends a lot, and I really enjoy talking to them. And I have like many delightful moments with them. Some are uh, not all moments are like filled with joy. There are some losses in my friends' families. So, but I'm always delighted to talk to them, even if I'm able to share joys or sorrows, no matter what. I'm always delighted to talk to my friends, and I'm always delighted to help you with anything you need for this class or even for any other classes. I know a lot of things, so if you need any help with anything, just let me know. Okay, I'm always here for you with this. Uh, I would like to conclude this session, and let me know if you have any questions. Feel free to email me. Bye bye.